Okay, so now we actually want to consider logs from a functional standpoint. For example, if I write something like y equals log base 2 of x, or if I'm looking at something like y equals natural log x, and again using function notation, I could say f of x, which is our y, equals log of x. And using our definition for what logs are, note this is going to be a base to an exponent, gives me my answer. Base here in this case is e, to exponent equals output, and I've got base to exponent equals this result. So if I rewrite all three of these using my definition of that log notation, I'm getting here 2 to the y equals x, e to the y equals x, and 10 to the f of x equals x. I want to look at those for a minute. That should look familiar to you. We've looked at exponential functions. The exponential case was 2 to the x equals y. Exponential here was e to the x equals y. And the exponential base of 10, 10 to the x equals y. So what have we done with this logarithmic business? If we set it up as a function where that logarithm of x is an output, f of x or y, if I rewrite that expression exponentially, what I've done is switched x and y from my exponential function. So therefore, drum roll please, yes indeed, the logarithmic function is going to be an inverse of the exponential function associated with it. Now we'll remember from our exponential function, our base here is going to be a positive number unequal to 1. So we could have a base of a third, we could have a base of a half, we could have a base of a quarter, we could have a base of 1.3, base of 7, etc. But by definition for exponential functions, our base is a number greater than 0 unequal to 1. So we know what y equals 2 to the x looks like. We've been graphing that now for quite a bit. We know it's going to rise from left to right. We know it passes through on the y-axis. The y-intercept is 1. So if I wanted to look at the function y equals log base 2 of x, that's going to be the inverse, because if I rewrite that exponentially, I've got 2 to the y equals x, and all I've done is switched x and y in my exponential case. And we remember then that our inverse function is going to be the original function's graph reflected over the line y equals x. So if I go through 0, 1 on 2 to the x, I'm going to go through 1, 0 on the log of x, log base 2 of x. And you'll note if I'm going down here, going down the negative x-axis and looking at a reflection across the line y equals x, I'm going to be going down the negative y-axis. If I'm heading up positively here, and I look at that reflection, I'm going to be heading up positively here. So my log graph basically has, as an asymptote, it's going to approach, as x gets closer and closer to 0, I'm going to approach the y-axis, and I'm going to grow. It's definitely an increasing function. As x increases, I definitely am getting bigger, but I'm going to get bigger a lot slower than the exponential function grew. So it's a slower growing function than the exponential function. Now, my domain for the exponential function 2 to the x, my domain was all reals, and my range was, my output y was greater than 0. So we know then for the inverse, for log base 2 of x equals my output, I know the domain and range are going to switch because I switch x and y. So my domain now becomes x is greater than 0, and my range then becomes all real numbers. And if you look at that graph of 2 to the x reflected over the line y equals x, indeed your domain are all positive values, and your outputs indeed could be all real numbers. And that should make sense. You should think if your output has to, or your x value, your input for the log function has to be greater than 0, because remember this x is going to be the value when 2 is raised to some power. If I raise 2 to some power, I've got to get a number greater than 0. So that should make some sense. And again, just to think about notation and what we've done with functions, looking at functions so far, certainly our exponential function is a one-to-one function. It passes the horizontal line test. It is a function because it passes the vertical line test. Functions that pass the horizontal line test that are one-to-one, 1x, 1y, have inverses. Note the log function as well is a one-to-one function. It's a function because it passes the vertical line test everywhere. It's a one-to-one function because, note, it passes the horizontal line test. So both the exponential and its associated logarithmic functions both functions are one-to-one. Both functions happen to be increasing functions if you look at it. For 2 to the x, as x gets bigger, y is getting bigger, and for the log function, as x gets bigger, y is getting bigger. So they're both one-to-one increasing functions.